In the previous lecture, we discussed about the mechanism of different types of nuclear reactions like elastic scattering, inelastic scattering, direct reactions, and most importantly, the compound nuclear reactions. Today, we will discuss another type of reaction, that is nuclear fission, which also undergoes through compound nuclear formation only, but nuclear fission and nuclear fusion, particularly the fusion reactions, utilized for production of energy, that itself is a subject. So I thought I would discuss them in more details. So today I will talk about nuclear fission and nuclear fusion reactions. So nuclear fission and fusion can be explained using the binding energy curve. What I have here is the binding energy per nucleon, that is called the average binding energy, as a function of mass number of the nuclei. And so you are familiar with this graph. The binding energy per nucleon is in the range of 7 to 8 MeV per nucleon. And if you see the fine structure, the binding energy per nucleon increases, then up to mass 60, it increases, goes up to almost 8.8 MeV per nucleon, and subsequently for higher masses, the binding energy per nucleon decreases. Now, if you recall the relationship between binding energy and masses, so binding energy was equal to ZmH plus NMN minus mass of the nucleus. So, higher the binding energy, lower is the mass. So that we can tell from here that nuclei which are around heavier side of, like in actinides, their binding energies are low, so their masses are more. In terms of, we can see in terms of the mass numbers, so you must have seen the mass defect can be positive or negative. If mass defect is positive, that means the masses are higher, binding energies are low. If mass defect is negative, that means the binding energies are high. So now in nuclear fission, what is happening? You split a heavy nucleus to two lighter fragments. Also in the process, the binding energy per nucleon is increasing. That means masses are decreasing. So there will be energy released. So this process will be exoergic. When you split a heavy nucleus of lower average binding energy to two heavy nuclei of higher binding energy per nucleon, then energy is released. That is what is nuclear fission. And the nuclear fusion reaction, you are fusing the lighter nuclei like deuterium, tritium, and forming heavier nuclei. Again, you are going from reactants of lower binding energy per nucleon to the products of higher binding energy per nucleon. So any process in which you go from low binding energy per nucleon to high binding energy per nucleon will be exoergic, and such reactions, nuclear fission and fusion, can be explained on the basis of the average binding energy curve. So what happens in nuclear fusion? Light nuclei like deuterium or deuterium tritium and so on fuse together to form a heavier nucleus, relatively heavier nucleus like helium, plus a neutron is emitted, and they have very high Q value. So around 17.6 MeV energy is released, which is primarily going to the neutrons. So neutron will in fact have 14 MeV energy, and the rest will go to helium. So this is there are different types of reactions where isotopes of hydrogen fuse together to form heavier elements like helium and so on, and in the process, a lot of energy is released. Then nuclear fission, the heavy nucleus captures a neutron, so 235 uranium captures a neutron, become 236 uranium, and which then splits into two fragments, and there are many such pairs. It is just one of the examples of a pair of fission fragments, but there are many such, maybe hundreds of such fragments are formed, binary fragments, and in the process again, sometimes 2, sometimes 3 neutrons are emitted, and a large amount of energy is emitted as the kinetic energy of fission fragments and other particles that are emitted in the fission process. So both these reactions, large amount of energy is released, and we will discuss shortly how to compare energy production from these two processes. So comparison of nuclear fission and fusion, particularly with regard to tapping this energy to produce power. So nuclear fission and nuclear fusion, if you see in terms of the energy released per nucleon, into nuclear fission, let us say assume 235 plus neutron, so you have 236 uranium, there are 236 nucleons, and 200 MeV is energy released. So per nucleon, 200 by 236, around 0.8 MeV per nucleon or per atomic mass unit energy is released. Compared to that, in nuclear fusion reaction, take the case of DT fusion. In DT fusion, 17.6 is the Q value of the reaction, and 5 nucleons are involved, 2 and 3. So per nucleon, 3.5 MeV is released. So per atomic mass unit, 3.5 MeV is released. So you can see, compared to nuclear fission, fusion has much more energy per gram or per nucleon of the target material. So it is having a positive point with regard to energy released per unit mass. Now, so that is the plus point of fusion. But in the case of fission, the fission can be induced by neutrons, neutral particles, or low energy particles. But in the case of fusion, as we are using the charged particles, it requires them to cross the Coulomb barrier. And if you recollect that 1 electron volt for 4 Kelvin, for 10 keV, almost 100 million degree Kelvin temperature is required. So that is the disadvantage. Nuclear fission gives rise to a large amount of radioactive fission products, some of which are very long-lived. And nuclear fusion also produces tritium and neutrons, but we don't have a long-lived radioactive isotope produced in nuclear fusion. In the case of nuclear fission, the nuclear electricity has been already being utilized. It is being produced for a long time, so it's a reality. Whereas the power or the fusion reactor is yet to become a reality, and so efforts are on to in fact tap the fusion power to produce electricity. So we will discuss both these aspects in the subsequent presentation. But before that, let's try to go down the memory lane, wherein how historically the fission process came into being. So you know, in 1932, James Chadwick discovered neutron, and it was soon realized that neutron can be captured by nuclei, and when a neutron is captured by a nucleus, you get by N gamma a higher isotope of that element, which is invariably beta minus active. And beta minus essentially gives you the next higher element. So Enrico Fermi at Rome very soon realized the importance of this particular concept of producing higher element using N gamma reactor. And he had in his mind how to extend the periodic table. At that time, the highest element known was uranium, element atomic number 92. And so if uranium 238 captures a neutron, then we get 239 uranium, which may undergo beta minus to give you element 93. So with that objective, he in fact started experiments to irradiate uranium-238 with neutrons and look for the radioactivity of the products that are formed. But Enrico Fermi was a physicist, and he did have 1 or 2 chemistry people in his group. So what they found that this particular reaction, instead of a particular one isotope having one half-life, they found several isotopes having, so there will be a lot of half-lives. And at that time, they did not have the gamma spectrometry set up which you can distribute between different isotopes. The one has to do the chemistry to separate different isotopes and count for the beta activity. So they were not in a position to solve this puzzle. What is the reason for, or which are the isotopes that are produced when you bombard 38 uranium with neutrons? But they had an idea that if element 93 is produced, it might decay by alpha, so that will become 91. That is protactinium, and again it can go further decay to by alpha to get elements radium. Actually, radium is 80, 86, 88, and this is 89. So these elements would be produced by the alpha decay of the element 93 and other elements. But they were not in a position to do any meaningful radiochemical separation to identify these radioisotopes. So then they established chemistry groups in Europe, in France, Irene Curie, Frederick Joliot, and Paul Savage started the experiments on bombardment of thorium and uranium with neutrons, and they were experts in doing radiochemical separations. So they were trying to separate actinium, for which they used lanthanum as a carrier because chemically they are similar. Lanthanum is lighter homologue of actinium. And so when they did the radiochemistry, they found some of the activities got concentrated with the lanthanum fraction. And so they have seen lanthanum as a fission product, but they did not do an unambiguous chemistry to establish this lanthanum. They were thinking it is actinium. At that time, Otto Hahn, in the same time period at Berlin, was studying again the same reaction, uranium bombardment of by neutrons. And again, they were focusing on radium. Radium could be one of the alpha decay products of higher elements. And that time they were using barium as a carrier to precipitate out radium. So they got the activity of radium with barium, but they wanted to make sure whether it is radium or barium. So what they did, they used radium-226 as a tracer to follow the path of radium, and then did the chemistry. And they found what they did is to separate barium and radium is a very, very tough task. So they did fractional crystallization of the barium and radium fractions, and they found that whatever they were calling as radium actually was barium. But they could unambiguously confirm, because the bombardment of uranium by neutron gives barium isotopes, not radium, because they have used radium as a tracer, 226 radium as a tracer, and activity got separated with the barium fraction, not with the 226 radium. So this was a landmark discovery in December 1938 by Otto Hahn and Strassmann. In fact, there is an excellent story behind this. There were old colleagues like Lisa Mittner. Lisa Mittner was working with Otto Hahn, and she had to leave Europe because of this Nazi movement. And later on in the United States, she actually, in fact, gave the theory of nuclear fission. So anyway, the Nobel Prize for the discovery of nuclear fission went to Otto Hahn in 1944. And the theory behind nuclear fission then was given by Niels Bohr in 1939. Very nice paper in Physical Review published by Niels Bohr. So the nuclear fission, the reaction, it can be even spontaneous fission, which we will discuss shortly, or a capture of a neutron by a heavy nucleus like uranium-35, giving rise to two fission fragments plus neutrons and large amount of energy. If you recall my discussion during the liquid rock model, from the energetics point of view, the liquid rock model can explain occurrence of fission by competition between surface energy and Coulomb energy of a nucleus which is deforming. So this is the diagram to explain nuclear fission. We have a nucleus as a liquid drop. So the liquid drop model will predict that the nucleus remains spherical in its ground state, because the surface energy will try to be minimized, and the surface energy of a sphere is minimum compared to the deformed nuclei. So the surface energy term tries to see minimum energy in the form of a spherical nucleus. Now, you know that fission is taking place, so the nucleus has to deform. This is the x-axis is the deformation, the degree of deformation. This is very symmetrical deformation, alpha 2. So when the nucleus is deforming, the surface energy is going to increase, Es. And the Coulomb energy is going to decrease because now the protons are a little bit apart from each other. So Z1, Z2 E square by D. So further apart the protons, less is the Coulombic repulsion. And so depending upon the nuclei, the delta Es and delta Ec, the change in the surface energy and Coulomb energy, then it will decide whether it can undergo fission or not. So the deformation energy, surface energy of a deforming nucleus in terms of the deformation parameter, this is the surface energy of a sphere, that is your As, a raised to 2/3, and this is the Coulomb energy of a sphere, Z square upon AC Z square upon a raised to 1/3. So the change in surface energy Coulomb energy will dictate whether the nucleus can undergo fission or not. So if you will see the ratio of delta Es, delta Ec upon delta Es at this point, when the nucleus becomes committed to fission, that can be written as in terms of Ec0 upon 2Es0. So basically you take 2/5 alpha 2 square Es0 and 1/5 alpha 2 square Ec0 and take the ratio, you will find Ec0 by 2 Es0 is the delta Ec by delta Es, and that becomes equal to AC Z square by A to 1/3 upon 2As a raised to 2/3, and which you can write in terms of Z square upon A upon a constant term 50.13. So this is called the fissionability parameter. Fissionability of the nucleus is dictated by this term. So higher the value of this fissionability parameter, higher is the fissionability of this nucleus. So the nucleus is undergoing deformation. So the shapes of the nucleus, like this is called the saddle point, like a transition state in chemical reaction. And once a nucleus is able to reach the saddle point, then it becomes committed to fission. And when the two fragments are about to separate, that point is called the fission point, about to scission, to separate the two fragments. So ground state, saddle point, and scission point, these are the three stages of the fissioning nucleus. So the fissionality of the nuclei, if you see that, like for example, for 238 uranium or 236 uranium, it will be 0.71 Z square by A upon 50.13. So that nucleus, if you see the spontaneous fission half-life, it will be very, very high, 10 power 14, 15 years. You go to californium 252 californium, X is 0.76. For 236 uranium, X will be 0.71. So slight increase in the fissionality parameter, from 71 to 0.76. The half-life is 2.6 years. For total half-life, but fission half-life is 85 years. T half for fission of 252 californium. So slight increase in the fissionality parameter leads to a drastic reduction in the spontaneous fission half-life. So this is the schematic of the phenomena that occur during the fission and the post-fission phenomena. A neutron is captured by the target nucleus, and you have the 236 uranium, which is excited. It can undergo beta minus decay to become the higher element, or it can undergo fission. So in the fission, the compound nucleus will undergo hibernation, deformation. So these are the like saddle point or close to scission point. And then because of the Coulombic repulsion between two fragments, you will have two fragments, a heavy fragment and a lighter fragment. And then this, so I am showing here binary fission because two fragments are formed. There could also be ternary fission also, three fragments are formed. Then these fission fragments are highly neutron rich. They have very high N by Z. So this, because of the high N by Z, they have excess neutrons, they emit neutrons. The binding energy of neutron is very small. So first they emit neutrons, prompt neutrons, out 2 to 3 fission neutrons per fission. Then if neutron emission is not possible, then you have the gamma rays, so neutrons, gamma rays, and then once by prompt gamma ray emission, they become fission products. The fission fragments by emission of neutrons and gamma rays become fission products, and the fission products will undergo then beta minus decay, and in the process there could be gamma ray emission also to end up with the stable endpoint. So this is the journey of the fission process from neutron capture by the two-third heavier nucleus to fission products and ultimately a lot of energy is emitted in the form of fission fragment kinetic energy, the energy of neutron, to gamma rays, energy of beta minus and neutrinos, and the gamma decay. After beta decay, there will be gamma decay from the fission product. So this is how the energy is distributed in different forms. A total that 200 maybe energy or a little bit more than that, you will find it is distributed in different forms here. Now let us go a little bit much deeper into the different aspects of nuclear fission. I will explain two processes, two observations. One is the mass distribution, second is the kinetic distribution. So mass distribution, that means what? As a function of mass, how the yield is varying. If you see from the liquid drop model point of view, the liquid drop model will predict a nucleus splitting into two equal halves, that is having the highest energy to be released. But what happens in this particular case of 235 uranium? You will find that we have a double hump barrier. That means the asymmetric fission is more probable. 117 is here. 117 mass is equal to the splitting of the nucleus into two equal halves. But that has got a very low yield. Yield means, out of 100 fission, how many times the particular pair is formed. So this is a fission yield curve where total area will be 200%, because 100 fissions are taking place, you will have 200 fission products. And the cross section for this reaction for 235 uranium neutron into fission thermal neutron is 583 bonds, which is very, very high. And the average mass of lighter and heavier fission products are 95 and 138 for 235 uranium. And the atomic numbers will be varying from 30 to 65 to 70 to 160 for lighter and the heavier mass peak. Yields are varying from maximum yield about 7%, minimum 0.001%. Very interesting thing I will tell you here, that if you see the 239 plutonium fission, then the heavier mass peak remains constant, and to conserve the mass, the lighter mass is shifted to heavier mass. Lighter mass product masses shifted to higher, and that it tells about the mechanism of the fission process. That means that the heavier side has got some fission products which have a very stable configuration, and so their yields are higher, and to compensate for the total mass, lighter mass peak shifts. So now for each mass, this x-axis is a mass number. For each mass number, there is a chain of isobars. Like if you take this pair is formed, Z1 plus Z2, 92, here iodine and strontium, you will find that there will be a chain of isobars. So the 138 iodine will undergo beta minus decay to xenon, to cesium, to barium, and so on. So until it becomes stable. Similarly, strontium 95 undergo beta minus decay to yttrium, zirconium, niobium, and finally stable. So whatever pair of fission products are formed in one fission process, they will start undergoing beta minus decay, and you can see the half-lives are increasing. The ones which are very much away from stability have short half-lives, and then by a chain of beta minus decay, all of them will come to stability. So that takes time. The half-lives are increasing. Some of the fission products have very, very long half-life, almost millions of years half-life. So another property of this fission process is the kinetic energy distribution. So I mentioned that kinetic energy of fission fragment is 168 MeV. So the total energy about 200 MeV, the dominant rho is taken care by the kinetic energy. So what happens when the two fragments are separating? This is what I have shown at the fission point. If it is a two equal fragment, both fragments are equal, that for symmetric fission, that is the mass numbers are same. So when they separate out, Z1, Z2 E square by D, the kinetic energy is released this much energy. Similarly, it could be a asymmetric pair, one light and one heavy, and then it could be slightly different. So normally, from the, if you see the spherical fragments, you would find the symmetric splitting will give you higher kinetic energy. If you see from Z1, Z1 equal to Z2, this kinetic energy is maximum. But if you see the actual observation as a function of mass number of heavier mass product, this is the symmetric splitting 118 to 36 by 2. So what they found experimentally, that the total kinetic energy is lower for a symmetric splitting compared to the asymmetric splitting where it is 200. So for mass number 132, the total kinetic energy is higher. Again, it cannot be explained on the basis of liquid trough model. And so the higher kinetic energy at 132 was explained due to the shell effects. If you recall the shell effects, those nuclei which have the magic number of nuclei, they are having spherical shape. And so if this heavier mass is around 132, then this is spherical. And once the nucleus is spherical, the kinetic energy will increase. Another observation that in the previous slide I found, I showed you that the mass number 138 is constant for different fissioning nuclei, 235 or 239. And that again, 138 mass having highest yield was attributed to a deformed magic number, deformed shell, neutron 88. So these are the kind of explanations, experimental observations of double hump mass distribution and total kinetic energy can be explained in terms of the nuclear shell effects. Okay, so ultimately when fission takes place, a neutron is captured by the heavy nucleus, and in the process you have two fission fragments and there could be 2 or 3 neutrons produced. Now this fission reaction, if it left uncontrolled, it leads to a device, nuclear device, atom bomb, which you can call, because these neutrons can subsequently induce fission in many more 235 uranium nuclei, and therefore it becomes a chain reaction. If you don't control, it means you don't suppress the neutrons, these multiplying neutrons will lead to a explosive device and the whole thing will explode in a very short span of time. That is the concept behind the nuclear device. But the same thing, if you control the reaction in such a way that for every neutron that is absorbed by a nucleus, at least one neutron is left to propagate the chain, then it becomes a controlled chain reaction. So in the controlled chain reaction, normally now when neutrons are produced, they will be captured by structural materials, they may escape from the device. So you may not have even one neutron left to sustain the reaction. So you have to have the reactor designed in such a way that at least one neutron is there available to sustain the chain reaction. That is the concept behind a nuclear reactor. In nuclear reactor, you have, if the fuel is in the form of pellets like uranium oxide, and which is now you have a fuel, the tube, and which inside you put the fuel pellets. So this is you have a fuel, the tube, inside the pellets are filled and you can cap it. So this lines are like this. And then you have the outside the fuel, there is a pressure tube, the coolant is flowing to take away the energy of the fission. So that fission, the heat, the coolant will be flowing, this coolant is flowing through this reactor, the pressure tubes, and then this heat, it will form steam. There is a heat exchanger. Heat exchanger will then take the steam to turbine, and you can run the turbine with the steam. So the whole process of fission ultimately leading to generation of steam, and then that steam running a turbine is the concept behind a nuclear reactor. So you require the clad, that means to keep the fuels intact, you have a cladding material, encasing of the fuel, then there is a coolant is flowing through the coolant channels. So outside the cladded fuel, you have another annular pipe through which the fuel liquid will flow. The coolant could be heavy water or light water. Fast reactor will be sodium also. And then you have the moderator also to thermalize the neutron, because thermal neutrons are more reactive than fast neutrons. So you need to reduce the energy of neutron make them thermal so that you have more fission reaction. And again, to control the reaction so that the reactor doesn't go out of hand, there are control rods. So the control rod will contain the neutron economy in such a way that there is no inadvertent rise in the neutron number at any point of time. In fact, as a function of time also, you will find the neutron economy will change and the control rods are adjusted so that the reactor remains as critical. So all this, the entire thing becomes the concept behind a nuclear reactor. So fission has been tapped to produce electricity, whereas and the nuclear device based on fission also has been reality, as all of you know. So this is the nuclear fission has been tapped for nuclear power production. In the next lecture, I will discuss about nuclear fusion, how it can be used for power, what is the status behind the tapping of fusion energy for electricity. Thank you very much.